Hello, George Romanic here. In today's video we will go slightly beyond pure geostrophic wind approximation and we will examine how the wind field evolves with time. You might ask, why is this even important? Well, one answer is that pure geostrophic wind approximation is diagnostic, which means we cannot use it to figure out how the wind field will look like in different moments in time. In other words, if you give me pressure field and latitude, then it is possible to calculate geostrophic winds. But it is not possible to say how these winds will change over time. And in atmospheric sciences, we want to know how winds and any field variable will change with time. That's called weather forecast. So the topic of today's video is on combining acceleration terms from horizontal momentum equations with geostrophic wind balance. Let's start. We saw that geostrophic wind components are UG is negative 1 rho F delta P delta Y, and the V component of geostrophic wind is 1 over rho F delta P delta X. And I hope you remember we got them by performing scale analysis of the horizontal Navier-Stokes equations at synoptic scales in mid-latitudes. We see that the pressure gradient force in the horizontal direction and the horizontal components of the Coriolis force are the largest terms, and when they are in equilibrium, we get geostrophic wind. Mathematical concept of real wind that is accurate to within 10-15% of real winds in the free atmosphere. The problem with these equations is that there is no time here, so we cannot say anything about how the system will look like in the future. To obtain prediction equations instead of these diagnostic equations, we have to go back to this table, infamous table, and include the next largest terms, and these are the local derivatives of two velocity components and the horizontal advection. They are 10 to power minus 4 in terms of magnitude. These are 10 to power minus 3, and look, all others are much smaller. So the inclusion of these terms will give us delta U delta T plus horizontal advection U delta X plus V delta U delta Y equals pressure gradient force and Coriolis force. And the same is for the Y direction. Now I will notice that this can be written as material or substantial derivative du in terms of U equation dt, but I will put here h to tell me that this is horizontal advection here and there is no vertical advection, and that will be minus 1 over rho delta P delta X plus Fv, and in the case of the second equation, dh horizontal. Now I will make use of these geostrophic expressions to rewrite the pressure gradient force in terms of geostrophic wind. Namely, from this expression over here, I can see that negative 1 over rho delta p delta y is equal f ug. And from this over here, I can see that negative 1 over rho delta p delta x is equal negative fvg. Now I will substitute these over here, and I will get that dhu dt is equal negative fvg, that's instead of pressure gradient force, plus fv. And similarly, d horizontal v dt is equal fug, that's instead of this pressure gradient force component, minus fu. Or the final blow is to rewrite this nicely as dhu dt is equal f v minus vg, and dhv dt is equal negative f u minus ug. And these are called quasi-horizontal momentum equations. These are beautiful differential equations, but there is one slight problem, and that is that the acceleration terms are proportional to the difference between actual wind and geostrophic wind. And I just told you that geostrophic wind is to very good approximation, good representation of real wind, which means this difference can be very, very small. That also means if something is very small, you better measure it very precisely to have accurate estimate of that quantity. In other words, acceleration is given by small difference between large terms, one being pressure gradient force and the other being Coriolis force. We can even demonstrate that using our infamous table. You can see that this acceleration is order of magnitude smaller than the pressure gradient force and Coriolis force in horizontal direction. So the balance between these forces, or disbalance rather, between these large terms is responsible for these accelerations. So you better be able to accurately measure velocity field and the pressure gradients if you want to use these equations. If you have errors in your measurements, and all measurements inevitably have errors, instruments are not perfect, then because these are two large terms, those measurement errors can influence your estimates of accelerations. To conclude, while this is dynamically correct, there is practical problem with using these equations because small errors in the assessment of these forces can result in large errors in horizontal accelerations. And therefore, we don't often use quasi-horizontal momentum equations in practical applications, namely weather forecasting. In today's video, we learn how we can construct simple prognostic equations using scaling arguments and still keeping alive to some extent geostrophic wind approximation. So we moved from purely diagnostic geostrophic wind approximation to prognostic quasi-horizontal momentum equations. While the concept is useful, simple to understand, it has very limited practical applicability because, as I discussed a few minutes ago, the acceleration terms in these equations are residual, small residual of very slight disbalance of two large terms at large scales in mid-latitudes. And these two terms are horizontal components of the pressure gradient force and horizontal components of the Coriolis force. Nevertheless, this is a useful concept. It gives us additional understanding of dynamical meteorology and synoptic scale motions. Until next video, goodbye.